Welcome to this briefing on the flight dynamics of the Albatros aircraft. This simulation-based project is designed to mimic the assessment and analysis that a test pilot would undertake before the first flight of this aircraft. We'll begin by verifying the aircraft's weight and center of mass using wheel reaction measurements to ensure proper balance. Thrust will be calibrated to gauge the static thrust of the engine based on RPM. We'll evaluate flight control surfaces and dynamic responses to confirm proper aerodynamic responses and control authority. Next, we'll assess the aircraft's flight performance including lift, drag and trim to ensure it's suitable for safe operations. Additionally, ground handling will be tested to verify maneuverability and avoid issues like oversteering. The goal is to provide a comprehensive analysis of the Albatros flight dynamics to inform a successful and safe test flight, ensuring the aircraft performs as intended. The initial assessment focuses on the Albatros's weight and balance. In the video, a highlighted circle represents the center of gravity CG, and the blue bar behind it denotes the mean aerodynamic chord. The longitudinal axis extends in front, and moving it forward shifts the CG backward, and vice versa. The simulation used the Flight Dynamics Lab Manager for this evaluation. The Albatros was positioned on 3 separate scales to gauge the mass distribution. With known landing gear positions, determining the forces makes it easy to calculate the moment arm and the CG, which varies from the initial test values. Adjusting the CG position along the longitudinal axis affects how the weight is distributed across each landing gear. By adjusting the test CG position incrementally, the total load is calculated by multiplying the measured load and the corresponding moment arm. The total moment and measured load allow us to find the measured CG. Plotting the measured CG against the initial test CG should ideally result in a line passing through the origin. Any discrepancies from this line are not significant. Understanding the nose and tail tipping points is crucial for determining safe CG positions. Exceeding a longitudinal CG of 0.2 causes the aircraft to tip backward, while a value of -4 leads to nose-down tipping. Thus, staying within these CG limits ensures the Albatros remains stable. After that, we will carry out the thrust test. The level of thrust that is produced in relation to the level of RPM input is indicated by a full Cessna that is positioned in front of the nose of the Albatros that is being displayed. In the case of the CG value of 0.05, the static thrust is displayed. It is possible to view the RPM on the flight display, which is located in the upper right corner. After that, the RPM is increased to 100%, and the thrust that was recorded is 30 newtons. This thrust data was captured at a number of various RPMs, and then it was plotted, which provides us with a sense of the static thrust, which varies across different points. After successfully configuring the input, it was necessary to reverse the direction of various control surfaces in this static control response. The correct control surface movements for the matrix are as follows: collapse down, low left, roll right, go left, your right, pitch up and pitch down. Page up and page down in the dynamic control response are in charge of regulating trim caused by the elevator on the keyboard raising the wind speed to a more sensible value. Here the trim is seen at the indication of the shift in pitch response and chrome angle are both consistent with lift and detail playing for CG and wind speed, respectively. The elevator can be used to observe the short-term response, which can also be observed for the seating position and wind speed. The data for this can be extracted into Excel. The Albatros was tested for its testicle page response across 3 different CD locations, 0%, 25 and 50 of the mean aerodynamic chord at 4 different wind speeds, to respond free stream. When studying the roll reaction, it is necessary to examine the manner in which the roll rate of the aircraft, in response to a fixed aileron input, fluctuates as a function of the free stream velocity being considered. In order to accomplish this, the roll response is determined for 3 different flow velocities, namely 10 meters per second, 20 meters per second, and 30 meters per second. At long last, an examination of the aircraft's yaw reaction is carried out. However, prior to doing this, it is required to confirm that the rudder deflection provides an angle of sideslip that is of the appropriate sign. As a result of the analysis of the yaw response, it has been determined that the damping in yaw is significantly lower in comparison to the damping occurring in pitch. When compared to a new pitch trim state, this indicates that the aircraft needs more time to adjust to a new yaw trim state prior to reaching a stable position. As anticipated, the breaker free screen speed showed a rapid overall rate. You can see that other free screen speed influences the Albatros given the input rate. Examining the dual input in this case enhances the damping of your reaction, which is less than the road's damping. The thrust line of the Albert against offset results in thrust page coupling. The CG location was moved along the vertical axis, and each experiment's angle for type change yield was noted. This information was plotted, and the location of the zero thrust pitch coupling, which was discovered to be at -0.03821-. First, 3 flap settings -0, 15 and 30 degrees are displayed together with the coefficient of lift v as the angle of attack of the aircraft. It is clear that 10 degrees of attack angle yields the highest coefficient of lift for all flap settings. According to the tests, an Albatros can lift as much as 1.3 coefficient of lift when its flaps are positioned at 30 degrees. By contrast, the datasheet indicates that flaps 30 will have a maximum coefficient of lift of 1.4 at an attack angle of 12.834 degrees. Following is the drag polar. One gets it by comparing the coefficients of drag and lift. Flap deployment obviously results in a larger coefficient of lift. Balancing the part of the curve where lift loss causes the coefficient of lift to become negative will yield the Albatros stall characteristics. It is only appropriate to examine the longitudinal trim now that we have covered flight performance. For this, several lift angles are presented together with the coefficient of moment at the center of mass v as the coefficient of lift for the default COM position of 0.058 meters from the leading edge. The plot makes clear that the curve with a 5-degree lift deflection goes through the origin. This implies that the best performance is guaranteed by an elevator angle of 5 degrees to trim. Slope of CMV-CL curves indicates an aircraft's longitudinal stability. Lingual stability of the aircraft is indicated by a negative slope of such a curve. The graphic makes clear that the aircraft is longitudinally stable at the COM points of 0, 0.2, and 0.35 of its mean aerodynamic chord. This further implies that it is unstable when the COM point is 0.6 of the mean aerodynamic chord. The static margin is 0 and the curve of the CMV-CL is flat and slopeless when the neutral point and the COM coincide. It is safe to conclude that the neutral point will be between the curves, whose slopes change from negative to positive between 0.35 and 0.6. Thus, one may calculate that the neutral point is roughly 47% of the mean aerodynamic chord. The steering and rudder input offer enough authority for maneuvering the Albatros on the ground, but high-speed steering can increase the risk of the wings touching the ground and place significant force on the nose gear, potentially leading to failure. The minimum speed required to lift off is 39 ms without flaps and 27 ms with flaps deployed, which is considerably higher than the predicted stall speed. At a cruise speed of 20 ms, achieving steady level flight requires the appropriate elevator trim and throttle settings. For this speed, an elevator trim of 40 degrees was required to maintain steady flight. The minimum trimmed flight speed was found to be 18 ms, while the maximum trimmed level flight speed was about 42 ms, needing a negative trim value. Additionally, the phugoid oscillation, which represents the long-period natural frequency of the aircraft, was tested to ensure the aircraft's long-term stability during flight maneuvers. Finally, once the Albatros is configured, we can validate its stability and performance by conducting a flight test circuit around the pylons at Landbeder Airfield. The aim is to maintain an altitude of 30 meters and a steady cruise speed of 20 ms throughout the flight, ensuring the aircraft's handling and control